All right, so in this video, we're going to be exploring the sampling distribution of sample proportions. And the way we're going to start this is we're going to mess around with this applet here at rossmanchance.com. This is going to help us build some intuition for how the sampling distribution works. Plus, it's kind of fun because we get to see these, little Reese's Pieces, pop out of this machine. So what we're going to do first is we're going to set the proportion of orange Reese's Pieces. I don't know if that's really a color for Reese's Pieces, but we'll say they're orange. 45% of them are orange. And in each sample, we're going to take 25 candies. And then we're going to see what our statistics are. So let's just show the animation first so we can see exactly what's going on. And you can see there, it's putting the orange on the left, all the other ones on there. And then it calculates that the sample proportion of orange Reese's Pieces, 0.48. Let's do it again. Let's see what happens. All right, going. 0.44 for the next one. We do it again. 0.48, and we can do that again. Exciting. See what's going on. We got a 0.46. So now we can start to see a little bit of differences, and we can start calculating some statistics like the mean and the standard deviation. So let's go a little bigger. Let's do 100, and we'll just we won't show the animation to save time, even though it is fun. Let's draw 100 samples of size 25, and bang, this is what we got. So we can start to see that it's looking like it's going to form some sort of normal curve. It's not perfect yet, but it's starting to get centered at actually close to 0.45. 0.45 is somewhere right here. And the mean of this is 0.454, standard deviation of 0.09. Now let's just do let's do 500. Wow, that looks pretty solid. Pretty normally distributed, pretty much centered at 0.45, and standard deviation 0.1. Okay, so now let's reset this. Let's clear that off. Let's see what happens if we increase the sample size to let's double it. Let's go to 50. And let's go ahead and we'll draw 50. Why is it not? Maybe I think I have to enter this first. Let's draw 100 samples of size 50. Try this one more time. Success. All right, let's see what happens. All right, we have a mean of 0.44 and a standard deviation of 0.068. And let's go ahead. Let's do another 400 so we can have about the same amount as we did last time. So we do bang, and we get a mean of 0.447 and a standard deviation of 0.073. So the means were about the same when we had the sample size of 25 versus this case was 50, but the standard deviation actually went down. It was actually 0.1 if you recall, and here it's 0.073. So let's see what happens now if we we'll just go ahead and take 500 of sample size 100. So we're going to take 500 samples of 100 Reese's Pieces at a time. Let's see what we get for our statistics. And look, the mean is pretty much right on 0.45. It's centered, right at the population mean. But the standard deviation even went lower. So the standard deviation was 0.049. So, it makes sense when you think about it. Standard deviation tells you how spread out the distribution would be. It gives you a sense. But it was decreasing as sample size increased. We went from 25 to 50 to 100. And that, again, makes sense. If we have larger samples, we're going to get more precise estimates of the population proportion, which is what we kind of touched base on in the first lesson. So now let's look at what happens if we But what if we have a different probability? What if we have a probability, let's say 0.5? Is that going to affect it? Let's go back to our original sample size of 25. Let's see what happens here. Standard deviation of 0.07, I mean a 0.15. So that worked out. Now let's see what happens when we have a sample size of 0.5. Or it's not a sample size of 0.5, a sample size of 50. So samples are size 50, and we're going to take another 500 of them. Standard deviation is about the same, a mean of 0.148. Let's go ahead now. Let's take a sample size of 100. Standard deviation went down again. It went down to 0.035. The mean is still about 0.15. Now let's just go even bigger. Let's see what happens if we go to 1,000. Hopefully this thing doesn't explode. Looks like it's being overloaded here. Ooh, I broke it. That looks pretty interesting. But wow, you can see the standard deviation even went down by a factor of 3.01. So again, the idea is that the concept behind this is that as the sample size gets bigger, the spread or standard deviation decreases. So we want to always think about what the sample sizes are, and we also want to think about what the proportion is. Like, it also depends on what the proportion is of orange. In this case, maybe it's 0.15. In other cases, it's 0.45. So we're going to explore that, and let's look at another example so we can explore that a little more. All right, so let's look at this example. Here we have 500 simple random samples of size 5 on the left here. So these are, let's put an n equals 5 so we can make more sense. Each sample is a size 5. And over here, each sample was a size 20. And we were looking at the proportion of pennies that were minted in the 2000s. The true proportion was 0.293. Now, they're both pretty much centered at the true proportion of 0.293. Like, 0.293 would be something like here, and this one would be like over here. So, we could say their means are the same, but we can definitely see a difference in the shape. This one looks more skewed to the right, where this one looks more normal. So let's look at another example. You can kind of understand what's causing that. Here we now take another 500 samples of size 5 over here, and then this size is 20. But in this case, we're looking at the proportion of pennies minted before 1976, where the true proportion is 0.092. And so 0.092 would be, maybe something like over here, and maybe over here for that. Now, again, you can see that there's, a distinct difference in how they're, shaped. The spread is smaller for this one. This one looks more precise, whereas this one is, you can see much more skewness. It's more peaked on the far left, where this one starts to, starts somewhat to, veer away from that. This is more symmetric than this one. It still has some work to do, but it is more symmetric. And so we need to basically recognize that the shape of the sampling distribution is going to be affected by the sample size and by the population proportion. When the population proportion is closer to 0 or 1, the sampling distribution of p hat is more likely to be skewed, depending on where if it's very small or very large. In this case, the the population proportion was very small, so it was skewed, to the right. But if it was the other way, if it was like 0.99, it'll be skewed to the left. So this is something that we're going to keep in mind as we go through the problems, or inference problems, actually, the course. All right, so all those behaviors lead to this. They basically lead to us being able to have formulas for the standard deviation of the sampling distribution of p hats, and us also being able to use normal approximations, but it has to satisfy certain conditions. Now, the first thing, the mean of the sampling distribution of p hat will be equal to the population proportion, and that's because if you remember earlier from the earlier lesson, the sample proportion is an unbiased estimator. So the mean of the sample proportion will be centered at the true proportion. Now, the standard deviation of the sampling distribution of p hat, and you're going to notice this notation. So sigma in the subscript of p hat, that's how we denote it. And let me point this out as well. So this is the mean of the sampling distribution of p hats. So the p hat again is the subscript. So the standard deviation of the sampling distribution of p hat is going to be equal to the square root of p times 1 minus p all over. This should be n. Whoa, I just caught myself a typo. All over n. Whew. This is only going to be valid as long as the 10% condition is satisfied, meaning that the sample can be no larger than 10% the size of the population. Now, we could explore the mathematics of why this is. It's not necessary for you to, understand that or even, explore that if you're in AP statistics. But it is fun, and I do like doing it because I love math, obviously. But it's not necessary. But there's usually going to be a section in the textbook, or you can always find some proofs on how this works. Anyways, so the bigger the sample size gets, the more approximate sampling distribution of p hats gets to be normal. So before we can, do any inference methods, involving normal calculations, we got to check that the large counts condition is met. So we want to check that n times p is at least 10. And that n times 1 minus p is also at least 10. Later on, you're going to hear this as being called like the number of successes and failures. And again, this has to do with the more, advanced math, binomial distribution, independent condition. But again, we'll talk more about that as we get, through the course. But for now, make sure that you're always checking this condition before you use normal calculations for your inference problems. Now, so the large counts condition, it's important because it's going to make sure that we can use normal conditions, we can use normal distributions to get our answers. Otherwise, if we can't, then our distribution won't be correct. It wouldn't make sense. It would be incorrect, probability calculation, so to speak. And the 10% condition, that has to do with, again, that our standard deviation formula will be, approximately correct. If we take too large of our population, so if we take more than 10%, then it leads to inaccuracy of the standard deviation of the sampling proportion of p hat. And it's kind of weird to think about because you would probably think that obviously the bigger sample you have is better, so it's better to have more than 10% of the population. But it's just that this formula isn't as accurate. In higher statistics courses, you'll actually use a little different formula with that'll have a correction error, I believe is what they call it. So anyways, let's go ahead. Let's now go through some practice problems so we can really understand how we use this stuff. Okay, so here we have that we say about 75% of young adult internet users, 18 to 29, watch online videos. And then, they take a sample survey where they have 1,000 young adult internet users, and they calculate the proportion p-hat in the sample who watch the videos online. So what's going to be the mean of the sampling distribution of p-hat? What would that be? And that would be equal to the population proportion, because it's an unbiased estimator. And let's practice writing this correctly so we can say the mu u sub p-hat, so the mean of the sampling distribution of p-hat is equal to the population proportion, which is going to be 0.75. All right, now what's going to be the standard deviation of the sampling distribution of p-hat? So as long as the 10% condition is met, we can use the formula on the previous page. So let's just flash back to it really quick. So you want to check that the sample is no more than 10% of the population, then we can use this equation. So in these types of problems, you kind of just have to use like your real world life sense, like you're not going to be like, well, you're not going to be able to do some like calculation where you can really figure out how many adult internet users, there are ages 18 to 29 and in the world or in the US, I guess in this case. But again, just use common sense. We can say reasonably that there's at least 10,000 of them. So this is, less than 10% of all the internet uses. So we would write this like, that n is less than or equal to 1/10 of the population n. So the population size. So then we were basically saying that n, the population, is at least 10,000. That's reasonable to say there's at least 10,000 people, or at least 10,000 young adult internet users ages 18 to 29. That makes sense. So now let's run the calculation. So the standard deviation of the sampling distribution of p-hat will be equal to the square root of the population proportion, so 0.75 times 1 minus the population proportion, 0.75, all over the sample size, so all over 1,000. And for that, we can just use our calculator. So 0.75 times 0.25 divided by 1,000. And we'll take the square root of this. We should get about 0.0137. All right, now part C. So now can we say that the sampling distribution of p-hat is approximately normal? So we got to check the large counts condition. So we want to check that n times p is at least 10, and that n times 1 minus p is at least 10. Now you may have hear this later on, or if you haven't already, this will be like also called like the number of successes and failures. So we just check to see that this is satisfied. So n equal to 1,000 times 0.75, and that's equal to 75, and so that's going to be greater than or equal to 10. And so then this works out, so we can check that because that's met. Let's check this. So n times 1 minus p, so 1,000 times 1 minus p, so 0.25. That will be 250, and that again is at least 10. So then we can say that this is also met. And so we're good there. And you're going to notice, so why it's called the number of successes and failures is because these two numbers will add up to, so this should be 750, whoops, sorry. These two numbers, my bad. These two numbers should add up to the sample size. So 750 plus 250 add up to 1,000. And again, you may have not heard it yet, but you'll hear that they also call it this number of successes and failures. And then now we now we can say that it's safe to to use a normal approximation to run a calculation if we were going to. Part D, if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? Okay, so let's first just do it, and then we're gonna kind of go into like the math and like the concept that we want to understand here. So we would simply just adjust our formula so that we would have 1,000 instead of 1,000 in the denominator. The proportion would still be the same. So 0.75 times 1 minus 0.75. We would get about 0.0046. Or to even be more accurate, 0.456435546. Okay, so you'd be like, what are they getting at here? Well, yeah, let's see if you still got your algebra skills. So if we look at these two equations, what's different is just the denominator on the inside of the square root. So what you can do here is we can rewrite this as the square root of 0.75. We'll just write the top as 0.25 there, over 9 times 1,000. Now, what am I getting at? So let's look at this now. We could write this as the square root of 1/9 times, and on top we can put 0.75 times 0.25. You can put that in parentheses to make it a little more clear. On the bottom we put times 1,000. So that's all the same, right? We can agree, it should be 0.25. It's 0.25. So 0.75 times 0.25, we have that there, times 1, it doesn't change it. In the bottom, we still have 9 times 1,000. And this can be rewritten as the square root of 1/9 times the square root of 0.75 times 0.25 over 1,000. Now, what's the point of this? What am I getting at? Well, the square root of 1/9 is just 1/3. So we can write it as 1/3 times what we had originally, 1/3 times 0.75, 0.25 on the inside over 1,000. And you're gonna see, because you're probably gonna get more problems dealing with this, that there's a common ratio between the standard deviation and the sample size. The sample size was 9 times as large as the original sample size, so it went from 1,000 to 9,000. Now, and as we know, remember we were looking at those distributions, and we saw that when the sample size increased, the standard deviation decreased. More data more precise estimates. And this essentially tells you a factor by which it decreases. So it decreases by the factor of the square root of 9. So it's not going to decrease, but it's not going to be multiplied by 1/9. It'll be multiplied by the square root of 1/9, which is 1/3. So this, is 1/3 times the original one, and you could just verify that. You could go to get an idea. 0.0137 times 1/3, and we get approximately that. And that's no coincidence. This is going to hold whenever we have this type of situation going on. All right, so let's look at one more. All right, so all this theory and conditions and whatnot is really leading up to us being able to do inference problems. So we can do inference problems involving population proportion when these conditions are met, when the large counts and 10% condition are met. So let's look at this problem. So the superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a four-year college or university. What is the probability that a simple random sample of size 125 will give a result within 7 percentage points of the true value? So she's going to take a sample of size 125. She's going to survey 125 of them, and she hopes to get a somewhat accurate estimate of what the true proportion is. Because again, it's very hard to it's very hard to survey everyone in the population. So we have to take samples. So if we want to find the probability of having, if you want to find this probability within 7 percentage points, let's look at what that would be in terms of 80%. We're basically trying to find, what are the chances that we'll get a sample proportion of about from 73 to 87%. So let's just write that clearly. Probability of p hats being between 0.73 and 0.87. Okay, so to find this probability, we have to have a standard deviation of what the sampling distribution would be. But before that, we have to check the 10% condition. So we have to check that our sample size is no more than 10% of our population. So I want to basically say, is it reasonable to say that there are at least 10 times 125 students at this four-year university? So let's just put that over here. That n is less than or equal to 1/10 of n. So we could pretty much say, yeah, like it's reasonable that this university, has 1,250 students. That's not that big. So reasonable to assume that n is, at least 1,250. So that's good. So now let's go ahead, let's run our calculation for the standard deviation. So we then could say that the standard deviation of the sampling distribution of p hat could be equal to the square root of our population proportion, which is going to be 0.8 times 1 minus 0.8 all over our sample size, which is 125. You can go ahead and run this times 0.2 divided by 125. And that would be about 0.0357. I guess we'll round to 8 since there's a 7 after that. Okay, so now we have to check to see that we can do a normal calculation, that we can, do a calculation, using the normal distribution. So we have to check then that the number of successes and failures, or n times p and n times 1 minus p, are both at least 10. So we got to check the large counts condition. So large counts condition. So NP is at least 10. And n times 1 minus p is at least 10. And so n, 125. P is 0.8. I believe that would be like 100. Let me just double check. I'm not feeling too secure about my math right now. Yeah, it's 100. So that's equal to 100. So that's, at least 10. So that checks out. We're good there. Now let's check this one. So 125 times 1 minus 0.8. So 125 times 0.2. And again, it's going to be basically, I know it's going to be 25 because this plus whatever I get here has the equal n. So let's just run it so you can see it's for real. Times 0.2 and 25. And so 25 is at least 10. So both of those would check out. So since both of these are at least 10, we can then use a normal distribution. So let's draw a little sketch. It's always going to have a visual, what's going on. So going back to, what we learned in chapter 2, we have a normal curve, or an approximately normal curve, with the mean of 0.8 and a standard deviation of 0.0358. So the center would be 0.8. And we're trying to find the proportion between 0.73 and 0.87. So 0.73, we could, we'll just say it's over here. And 0.87 over here. We know that's going to be about 2 standard deviations away, because our standard deviation is 0.035. 0.035 times 2 is about 0.07. So we're trying to find the area of this shaded region, essentially. And so we can, now just rely on our technology here. So we go to distribution, normal CDF. We're going to enter our lower bound first, which will be 0.73, comma, our upper bound, 0.87. And then we're going to enter our mean, which is 0.8, and our standard deviation, which is 0.0358. If you have some more advanced calculators have it, really simple. They have it like listed, but this is the syntax for this. So make sure you memorize. You don't have one of those calculators that has, nice and easy for you. We run this and we would get a probability of about 0.946. And let's write that we use our, we use the command. And on your AP test, it usually wants some work to show that you use a calculator. So we could say something like, we use the command normal CDF, 0.73 as our lower bound, 0.8 as our upper. Let's just carry this over to another one. Our mean of, or sorry, not 0.8 as our upper, 0.87 as our upper bound, followed by our mean of 0.8, and our standard deviation of 0.0358. This gives a probability of about 0.949. As we get closer to the AP exam, I'm going to, be more clear. We're going to practice more formally how the readers want your answers. For now, right now, we just really have to learn the concepts. We really have to just focus on making sure that we understand, the concepts behind this problem. And so we can then just say that, that there's about a 95% chance that if you were to, draw samples of size 125, that you would get, one where its proportion, would be 0.73 to 0.87. You have about a 95% chance. I mean, let's just write the formula because that kind of didn't sound right the way I said it. So about 94.9% of all simple random samples of size, because again, a sampling distribution is specific for sample size. So size 125 in this case will give a sample proportion between 0.73 and 0.87. All right, so there you go. There's an overview of how we work with sampling distributions of population proportions. In the next lesson, we're going to look at what we do when we're dealing with means. So I'll see you then.